Now we're going to talk about polymerization. So polymerization, if you've ever watched Yu-Gi-Oh, it is the same thing. It is literally taking small individual molecules and linking them together to form larger, bigger molecules. Now, obviously in the cartoons and in anime and things like that, they usually merge themselves into a larger, stronger, different thing. In chemistry, it's not so exciting. We basically take little individual chains that we call single units or monomers, mono meaning one, and we form them or link them up to make a polymer, poly meaning many. Okay, and there's two types of polymers. There's natural polymers, like the types that we find in nature, so proteins like in your muscles, starches like carbohydrates, and cellulose like wood are what are natural polymers, and they're part of the reason our muscles are so as strong as they are, and they're also the reason carbs are usually can store as much energy as they do, and the same reason that trees or wood can be as strong as it is. Okay, and so those are natural polymers. Synthetic polymers are things like plastic, nylon, vinyl, or Kevlar. These are all made from oil-based, well, nowadays there's multiple options, but typically these are made from oil-based products like gasoline. Well, not gasoline, but the actual material that gasoline comes from. We're going to call it petroleum. It's typically made from that. And synthetic polymers are also very light and very strong. If you compare a, plastic bag for a paper bag, the amount of weight that the bags can carry before they rip compared to the amount of weight that the bag itself weighs. The plastic bags, I know we ban them, but the plastic bags are much stronger per weight unit than the paper ones, or at least the paper ones that are around now. Maybe they'll make better paper bags, but I don't know if they'll be as light as a plastic bag and still be able to hold as much. But those are our two types of polymers. Now, what do we do and how do we draw it? It's real simple. For polymerization, you're basically going to do two types. There is condensation polymerization, and if you know what the word condensation means, right? Condensation, if you ever see it, like when you take a shower, the fog that builds up on the mirrors and the glass, that's called condensation, and that's water. So condensation polymerization is where we remove water. So just like the esterification reactions, we do the exact same thing. We take the H from one, in this case it's an N, we take the OH from the other end and we remove a water. And then what's left over bonds together. So this thing would look like this. Now, I didn't draw out all my H's. I can go in and fill them in. I was just trying to keep it the same format as I did on the left side to make it a little bit easier to view it, but that's it. Now, this does not count as a polymer, okay? This is barely, most people would not count this as a polymer. This is just merging two monomers together. To be a real true polymer, you need to do this like 20, 30, 50, 100, several thousand times. So you're gonna have to make a much bigger molecule than this. And so that actually will lead us to, how do we draw polymers? Because if they're that big, they're gonna take all day to draw. And I'll get back to that in a second. And then the last type of polymerization is addition polymerization, which if you remember organic addition, and if you don't, you can go back and watch that. Well, it's the same thing. It's just organic addition on a large scale. We take one of the two bonds, or if you had triples, it would be one of the three bonds. We break them, and then we link together the things that are a bond short. Now, in this example, there would need to be more of them because I'd have to now link this together with something, and I'd want to link this together with something, and you'd go out bigger, but I only drew three, so we're just going to go with that. And so it's going to look like this. And if we drew it the way Table R would draw this, right, using their format, it would look like this. It would say these two would go out to more carbons and would be of varying lengths. If I said R and R, that would imply that the chain on the right side would have to be the exact same length as the chain on the left side. So by saying R and R prime, or R1, whatever you want to call it, that's telling you that this chain could be, 500 carbons long and this chain could be 2 carbons long. It doesn't matter, they don't have to be the same length. And so that's the way it would look like if it were drawn based on Table R. And now, how do you draw them for how do you shorthand and draw these molecules? It's simple. You take the repeating pattern, the pattern that repeats most frequently, right? Or the smallest repeating pattern you can find. In this bottom case, it's this, and in the top case, it's this, right? And then you just put an N outside, and the N is the number of times it repeats. So that's how you do polymers. So you would take their monomer form, right, or the smallest repeating unit that you have. In this case, it's a little larger. And then you would just write a number outside. That number could be 10, it could be 100, it could be thousands. And that's the way you don't have, so that way you don't have to write the whole thing out because it would literally take all day. So that is polymerization.